Question. A wire frame AOPQB lying in the horizontal plane is free to rotate about a vertical axis passing through C, center C, of the same circle and perpendicular to the plane AOPQB. The mass m of the frame is uniformly distributed over its whole length. Moment of inertia of the frame about this axis is OA, QB are R, CP is again R, the radius of the semicircular part. We want to calculate moment of inertia about this axis, about this particular point. So here the mass is distributed completely. So we can consider linear mass density lambda as equal to total mass divided by the total length. That is equal to 2r, that is this r plus this r plus pi r. Now, moment of inertia of AO about point C. First of all, moment of inertia of AO about the center will be I1 equal to ml square by 12 plus we have to shift the axis to this particular point. That will be ml. L is the distance from here to the corner. If you take that is equal to L by 2 plus this L or R we can consider. So it is R by 2 plus R. That is 3R by 2. So moment of inertia of AO. Also we can consider as BQ. It is the same thing. This is, let us call I1. We will use the formula moment of inertia about ICM plus ml square. L is the perpendicular distance from the axis of rotation to that point. So I1 we can write it as, let us put it in terms of lambda. Lambda into R square by 12. Okay, this is the moment of inertia about center of mass. Plus m. M is nothing but again lambda into R into L. What is L? Now R by 2 plus R. That is 3R by 2. 3R by 2 whole square. That is 9 by 4 R cube. So lambda R cube if I take in common. 1 by 12 plus 9 by 4. That will be 7 by 3. So 7 by 3 lambda R cube. This is the moment of inertia of part AO as well as for QB. Now let us calculate moment of inertia for the curved part. Moment of inertia of OPQ. Let me call this as I2. What is I2 equal to? M. This is mr square for the ring. Okay, the mass is only m into this pi r. So lambda pi into r into the radius r square. So how much you'll get? Lambda pi r cube. Now we know I1 and I2. So total moment of inertia will be I1, I2 plus I1. So 2I1 plus I2. Let us substitute it. So what is I1? 7 by 3 lambda r cube. So this will be 14 by 3 lambda r cube. Plus this will be lambda into pi r cube. So I think we can take lambda pi r cube here common and rest all we can substitute here. So I will be equal to 14 plus 3 pi divided by 3. Remaining lambda r cube. Finished. This is the moment of inertia. Now since we have chosen lambda value, I will substitute the lambda value also here. So 14 plus 3 pi divided by 3 into r cube into lambda. What is lambda? Lambda value will be equal to m divided by 2r plus pi r. So r we can take it out, cancel it out. So we can get this value as total 14 plus 3 pi divided by 3 pi plus 6 into remaining mr square. This is the moment of inertia of the figure which is shown with AOPQB as the thin rod. So correct option will be 14 plus 3 pi by 3 pi plus 6 into mr square. Mr square 14 plus 3 pi by 3 pi plus 6. So option A is correct option. Mr square pi plus r by pi plus 2r. This is wrong option. Mr square 3 pi by 4 wrong option. 1 by 2 mr square wrong option. So mr square 14 plus 3 pi by 3 pi plus 6. This is the correct option. So what we have done is clear. First we have taken mass per unit length. Then moment of inertia of AO we calculated. Moment of inertia of BQ we have calculated. Moment of inertia of AO or BQ is calculated as moment of inertia about the center of mass plus the total mass into the perpendicular distance from the axis of rotation. That we call it as I1. Similarly, moment of inertia of the ring we have calculated. Now substituting these two values and simplifying, we get the answer like this.